Hello, my name is Diego, and this is my lab 3 for Physics 2211. So just a quick table of contents about what we're going to be talking about. So we're going to go into an introduction and purpose of the lab, the laws and concepts used, the procedure, and then the results from both parts, errors, conclusions, and findings. So the purpose of this lab was to create a computational models of ships and stars that motion around a black hole with the goal of discovering the mass of that black hole. And then what we wanted to do with that was then create a unique version of a ship that would orbit around it, but not crash into the moon. So some of the laws and concepts we use in this lab were Newton's second law. So F equals m times a, universal gravitational formula, which is F grav is equal to G m1 m2 over r squared in the r hat direction, in the negative r hat direction to be specific, and the position and velocity update formulas shown below. So the procedure for this lab was to use Gloster, which is a coding program that allows us to find forces and masses and use a bunch of calculations to find that mass of the black hole. And so the results for part one. We use a gravitational constant that we've learned in class. And this is just setting up an initial conditions. And then we have a mass of the star that we used. And then we have the time interval. So this is our like delta t, and this is what the interval is between every point that we're going to be using to find the average for the mass. So this is how much it's changing per step. And so to find that, we basically did the change of momentum kind of thing. So we set up a loop where we have our vectors initial conditions with a vector like a velocity and a velocity final. And the way we did is we used the mass of the star and the velocity initial and the velocity final to find the momentum for the initial and the end. And then from there, you can find the change in momentum and the change in velocity. And then from there, you can find the force, which is dp dt. So it's delta p over delta t. So that's what we found here, change in potential momentum over change in time. And then we got our net force there. And so to continue that, what we did with that net force was we found the F net perpendicular and the F net parallel. And so what that'll help us do was help us find the mass of the black hole by taking the averages of those types of forces. And then what we were to do with that was to change the position of the star as it trails around that black hole to help us to visualize it, basically. And then lastly, we created a bunch of stars and axes and arrows that will point into the direction that will help us also visualize that. So if we go back here, this is what it looked like at the end. The results for part two. So the first thing was to initialize a little bit, but I actually did it kind of opposite. So I did this at the end once I found out all my forces and whatnot. So I found that to be easier. But what we had to do was to find the total forces by taking the displacements of the moon and ship. So we're looking at the forces acting on the ship, the forces acting on the moon, and we wanted to take those and total those onto the F net of the moon on the moon and then the F net on the ship. And so we got two different kinds of forces. And so what we did was we did the F net for both. So we did like the gravitational constant, the mass one, mass two divided by the magnitude of the length and put it in the r hat direction. And so we did those calculated the forces on things. And so we just did that repeatedly, and then we were able to move things because of that. That was it. Just some possible errors that could have happened during this presentation were the glow script coding errors. And so this is an older platform, so it could have maybe errored out a couple times. So yeah, and then the conclusion for this. So in order to find the total normal amount of forces on something, so like on a system, you must know the net amount of external forces acting on that thing. And then we found that the mass of the black hole was 5.8 times 10 to the 35th kilograms. And so that was done by running that first part one code and then taking all of those points and finding the average of that. And then a quick what if question is what if there were two black holes instead of one? So the gravitational effects of those would have combined. So whatever mass we calculated would have represented the sum of those two black hole masses. Thank you.